Welcome to Planes Overhead, guys. So today we're going to do landing distance calculation for the A320 performance section, that is. We generally calculate factored landing distances to give a safety margin, as it is more conservative in nature, so that you get more room for safety. And in this video we shall be discussing steps to find out factored landing distance with single failure. So in the next video I'll do multiple failures, which is much more complex and perhaps more interesting, but this is pretty straightforward. So let's begin. So steps, pretty straightforward as well. Note the weather data for the airfield. Use the runway condition assessment matrix to determine the code. Select the flap setting as requested by ECAM, or the crew can also choose it at their own discretion. Determine V approach and determine factored landing distance. So keep the QRH in handy. All this is from the QRH only. So this is the question that we are going to work on. So kindly note this down. Find the landing distance for the following conditions for the Airbus 320 at 25% CG. Green system, low pressure is the failure that we are dealing with. It's a hydraulic failure. One thrust reversers in operative. Elevation of the airfield is 700 feet above mean sea level. Gross weight 60 tons. No runway slope. Flaps 3. Runway 11 conditions are wet. Temperatures 2-3. And winds are 10007 knots. So this is from the QRH runway condition assessment metrics for landing. So runway condition was given as wet up to 3 millimeters of water. So the code that we find out is number 5 and level good. Alright, so just keep this in mind. This is used to find out what table you will use to find out the landing distance. Alright, so once that is done, then we can go to the next step, that is determine the V approach. Now V approach has a particular formula to it, and the formula to V approach is Vref plus delta Vref plus approach correction. Alright, so Vref. Now Vref comes from this table that is here. So Vref is equal to VLS in config full. Our CG was given as 25% and weight was 60 tons. So this lies between 58-62, which comes out to be 130 knots. Now keep in mind that this is for config full, and we have decided that we are going to do a config 3 landing. Now for config 3, how do we find out? So config 3, there's something called as the delta Vref correction. Now how do we find out that is referred to the applicable landing distance table. So we open the landing distance table for that particular failure in the QRH. So this is the QRH landing distance table for hydraulic system. Code is checked 5, level good. Green system, low pressure. Flap 3, config landing. Delta Vref turns out to be 6. Okay, so this is very important, so keep this in mind, and when we go down here we keep a note of this 6 knots. So delta Vref comes out to be 6 knots. The next step is find out approach correction. Now approach correction, now our delta Vref was less than or equal to 10 knots, which was 6 actually, so we'll consider this part of the table. Approach correction equal to highest of 5 knots in case of auto thrust on, so auto thrust is on. 5 knots in case of ice accretion in config full, we don't have config full. 10 knots in case of ice accretion in config 3, we don't have ice accretion at all. Or 1/3 of headwind component excluding gust, maximum of 15 knots. So 1/3 of headwind component, our headwind component was about 5 knots, so 1/3 about 1/3 of 5 knots is approximately 2 knots. So 2 knots, so the highest of 5 knots and 2 knots, which comes out to be 5 knots because auto thrust is on. So approach correction is 5 knots, and approach correction plus delta Vref must be limited to 20 knots. In this case it is 11 knots, as you can see, so it is limited to 20 knots. And if your delta Vref was say 10 to 20 knots, then we'll apply this. If it was greater than 20 knots, we would apply this. So now the V approach is 130 plus 6 plus 5, it gives us 141. So our approach speed is ready. Now landing distance correction, speed column in the landing distance table. Point 1, if approach correction is equal to 1/3 of headwind component, no speed correction. So our approach correction is 5 knots. Our 1/3 of headwind component was 2 knots. So this is not applicable to us. If approach correction is greater than 1/3 of headwind component, yes. So approach correction was 5, headwind component was 1/3 of headwind component was 2 knots. So the speed correction is equal to the approach correction. So we have to add this into the landing distance correction, which I'll explain to you. Caution: any extra pilot approach speed increment must be added to V approach and must be taken into account in speed column for landing distance computation. So this is very important in case the pilot is adding some speed increment just to have safety margin. So then that must be catered for the landing distance computation. and if not applicable is displayed in the speed column of the landing distance. Do not add any extra pilot speed correction because it's already catered for the distance. Alright, so next step we find out determine flaps and factored landing distance. Flaps have been already determined. We are doing config 3 and factored landing distance. Green system, low pressure, hydraulic system. This is in the QRH again. So config 3 landing. Reference distance is 1910. I've written it down here. Now weight correction per 1 ton above 66 tons. Now this table is made for 66 tons. We have a weight of 60 tons. So weight correction equal to subtract 10 meters per 1 ton below 66 tons. So our weight was 60 tons. So 66 minus 60, 6 into 10 minus 60. Okay. Now speed correction per 5 knots. So our approach correction was 5 knots exactly. So we'll add 160 to it straight away. Suppose say it was say 10 knots, then we would have added 320. Any pilot approach speed increment also is being catered by this column only. Okay, so if you the pilot adds extra 5 knots, then you have to add further 160 knots. 160 meters, sorry. And altitude correction per 1000 feet above sea level, we add 100 knots. So this elevation was 700 feet, so I've added 70. There is no tailwind. Wind correction per 5 knots of tailwind, so there is no tailwind. Temperature per 10 degree above ISA. So at 700 feet, the temperature is supposed to be 13 degrees approximately. So the temperature given in the weather data was 23. So we add 100 to it. Okay. So there is no downslope. There's no runway slope. Per thrust reverse is operative minus 90. So one was operative minus 90, and no overweight procedure is applied. So this comes out to be 2090. Now the formula for factored landing distance is landing distance into MEL landing penalty factor plus the safety margin. Now safety margin is Airbus recommends 15% safety margin. Okay, so some companies may have a different policy, so kindly check with that. And safety margin, we are just going to do Airbus one, 15% here. And MEL landing penalty factor is some failures have certain MEL requirements which lead up to landing distance change. So I will just show it in the next slide an example so that you can relate to it. So in this case anyway, there is no landing penalty factor from the MEL minimum equipment list, that is. So landing distance is 2090 is what we found out, and there's no MEL penalty factor, so it's nil, plus the safety margin of 15%. So 15% of 2090 is 313.5, and that comes out to be giving us a total factored landing distance of 2403.5 meters. So that is our factored landing distance, and this should be within the landing distance available on the Jepson landing runway chart. Landing distance available beyond basically glide slope, or even you could just consider full length in case of critical emergencies. All right, so once this is done and we are done with the calculation, I just wanted to show you an example of the MEL, the landing distance performance. So I've just taken up a spoilers 103 fault, and this is from the MEL. So as you can see here, landing performance computation, multiply the landing distances by 1.05. So if in case there was a certain failure where you have to check an MEL, you will have to add that distance to the landing performance. So you might have to use it here 1.05. All right, so that's all on this video. Pretty simple, I would say. We will do the several failures in the next video. So thank you for watching, guys. Subscribe to the YouTube channel and like the Facebook page for regular updates. Give the video a thumbs up if you like this video, and do not forget to share it with your friends. Comment below if you have any doubts. I'll surely get back, and you can always reach me through these links on your screen: YouTube, Facebook, WhatsApp, and email. Cheers and happy line, guys. Have a great day. Take care. Tada. Bye.